Good afternoon, everyone. I hope you're all well. Dr. Bennett here, and in today's class we're going to be talking about centers of mass. So in the previous couple of classes we've been talking about centroids of lines and areas and volumes, and a center of mass is nothing more than a centroid of the object's mass, because what we're interested in doing here is representing an object's weight as a single force vector acting at its center of mass, so that we can go ahead and apply our statics analysis and resolve the forces that are acting on that particular object. So what we have down here is a sketch of this arbitrary blob which has mass little m, and if we split up that blob into little pieces with which each have mass dm located at the position x, y, z, we can find the weight of each of those little pieces as the mass, which is dm, multiplied by the acceleration due to gravity, right, g. And that's in the negative y direction, right, because weight always acts vertically downwards. So that's where this negative j component comes from here. So what we can do is find the total weight of this arbitrary blob by taking the integral over the whole mass of these small pieces, right? So we have the integral over m of negative gj with respect to m, right? So if we integrate that with respect to m, we get the following, right? Negative mgj, and as we've just said, mass times the acceleration due to gravity is just weight, right? So we just have this negative w acting in the negative y direction, right? Because it's acting vertically downwards. So the other thing we can do is work out the moment about the origin due to these small pieces, right? As we take the position vector from the origin to the point where the little piece is, r o dm, cross product that with the weight vector of the little piece dm, so we get the cross product. So we set up here the little piece dm is positioned at coordinates x, y, z, so our position vector from the origin to the little piece dm is just given by x, y, z, right? Because we take, to get the position vector, we take the position of this piece, subtract the position of the origin, right? And then down on this row we just have the weight vector, and as we just said up here, that's negative dm multiplied by g. So if we work out that cross product, we get the following, right? We have two components, one in the I direction, one in the k direction, and we should recognize that that is a sensible answer because the cross product gives us a vector that's perpendicular to both of these things, right? So to find the total moment then, so remember this here was the moment due to each of these individual dm pieces. To get the total moment, we just integrate this over the whole mass, right? Which is what I've done here. So if I integrate this with respect to m, I just get m's in both of these terms. And if I get m in both of those terms, I get these mg's floating around, which, as we've said a couple of times now, mass times the acceleration due to gravity is just weight. So I can write the total moment due to this whole arbitrary blob is given by this expression here. So now let's consider a single weight vector acting at the center of mass of this arbitrary blob. So by the way, going forward now, I'm going to start abbreviating center of mass as COM. So what I've done here is I've drawn the same arbitrary blob, I've drawn on its center of mass, and I've given it a weight vector, negative WJ, right? And I've said that the center of mass is at coordinates x bar, y bar, z bar, okay? And then I've used that information to do exactly the same thing as I did up here. I've calculated the total moment about the origin due to this weight vector, right? So what I do is I take the position vector from the origin to the center of mass, which is at x bar, y bar, z bar, and cross-producted it, if that's even a word. I've made the cross product with that position vector with the weight vector which I had over here. So I get the following determinant to solve, right? So the position vector again is just given by the position of the center of mass, subtract the position of the origin, which is just x bar, y bar, z bar. And then the weight vector is just negative w in the j direction, right? So I get this. Now look what we have, right? We have the same thing, right? If we consider our initial position up here of all of the individual pieces, dm, so basically what we're saying is if x, y, z is in the same place as x bar, y bar, z bar, then the total moment of these two things are the same. So what we've done is that what I've summarized down here is that we've proved that we may consider the weight of an object acting at its center of mass, right? So what we can do now is go ahead and formulate these integral equations for the center of mass, and you'll realize or recognize that they look pretty much exactly the same as all of the other centroid formulas that we've derived in the past couple of classes. So the x-coordinate of the center of mass is just given by this integral equation. We take the integral over m of x with respect to m, and then we average that across the whole mass by dividing through by the integral over m of dm. And I've spared you the y bar and z bar coordinates because they're exactly the same, right, as we've seen before. Or what we can do as an extension to this is, if we remember that mass is equal to the density, which is given by symbol rho, multiplied by the volume, we can rewrite these integral equations in terms of rho and v, right? So these are the integral equations we're going to use for the center of mass in the examples to follow. But before we do that, we need to have a look at a couple of special cases where we can reduce this system down for a couple of simplified examples. Oh, and by the way, good news is that I've managed to get myself some green apple flavored Gatorade. So things are looking up. So these are the special cases. So the first one is that for a homogeneous object, and homogeneous means a constant density, the center of mass is the same as the centroid of its volume, right? So you remember we looked at centroids of volumes where we assumed that the mass of the object is constant. So that's just what we're saying here, is that if we have an object with constant density, or we're dealing with an object that's made up of the same material throughout, we can just calculate its center of mass just by finding the centroid of the volume. The second case, the second special case, I'll get my words out in a moment, is that if we have a plate of uniform thickness, like this poor sketch over here, then the center of mass is the same as the centroid of the area, because the material's homogeneous and the thickness is constant, so we can just find the centroid of this area of the front face here. So that should be fairly intuitive to you as well. And the final special case is that if we have a homogeneous bar of uniform cross-sectional area, right? So it has the same cross-sectional area along its length. It's made up of the same material, so it has constant density. Then we can find its center of mass by finding the centroid of the line that goes through its axis. Now that's a lot of words to basically describe something that's hopefully quite intuitive to you. So let's go ahead and have a look at a couple of examples now. Okay, so in this first example here, we're looking at a cylinder or a bar of length L and constant cross-sectional area A in a 3D coordinate system. So think along the lines of what we were talking about down here. But we have this non-uniform density. So the density of the bar, for whatever reason, depends on x, right? So it's a function of x. So as the bar goes along the x-axis, its density changes, right? And it changes according to this formula here. So the question is to find the center of mass of this bar, right? So as we've just discussed, the center of mass, or the x-coordinate of the center of mass, is given by this formula here. And I've chosen this formula rather than this one because we have to deal with this non-uniform density, right? So that's how I've started off the solution. I've written down this equation which depends on rho, which is the density. And then what I've done here is recalled that the volume is the same as the area multiplied by x, right? So it's the cross-sectional area multiplied by the length, right, which I'm calling x. So that's how I've rewritten this integral, and also the denominator as well. So that then gives me an equation where I can plug in this non-uniform density rho. So from here to here, all I've done is just replace rho with this expression here on both the top and the bottom. So I'm integrating over the whole length of the bar, which we're told has length L. So I'm integrating between 0 and L. And then I have this expression in here replacing rho. I could also go ahead and write down the cross-sectional area of the circle or the bar, right? Pi r squared. But as you will see in a second, because it's constant, I can bring it outside the front of the integral, the same as rho 0, which is also a constant, and that cancels anyway, right? So I'm just left with these two integrals to calculate. The top one is the same as the bottom one, apart from it's multiplied by this extra x here, which comes all the way back from over here. So I calculate these two integrals, should hopefully be fairly straightforward to all of you, and I get the following, right? So hopefully you can all replicate that and integrate these two expressions to get this. And then I just plug in L because I have zeros here and that all cancels, and I'm left with the following expression. So I tidy those fractions up, cancel the L squared with the L, and I should get 5/9L. So the x-coordinate of the center of mass of that bar is actually greater than halfway along it, right, because of this non-uniform density. So if it had constant density, the center of mass would be halfway along it, right? But because the density changes as we go along, this x-coordinate of the center of mass is greater than halfway along it. So that's the first example. The second example that we're going to have a look at is basically revisiting something that we've seen a number of times before, i.e. an example to do with supports, right? But now we're going to include the mass of the bar. So you remember up to this point in the course, what we've done is assumed that the forces acting on this bar is much greater than the mass of the bars themselves, and therefore we've neglected the weight of the actual structure itself. You'll remember we've done that when we're looking at supports, and also when we went on to discuss trusses at length, right? We neglected the weight of the beams and the members. Now we're in a position where we can actually include that in our calculations, right? So we have this example here. We have this L-shaped beam or bar structure supported at A with a pin support and at B with a roller support. It's 1 meter long and 1 meter high. And we're told that this L-shaped bar is 80 kilos, and we want to revisit something that we've looked at before, i.e. we want to calculate the reactions at these supports, but now including the weight of the bar itself. So the first step, as always, is to draw a free body diagram. So I've drawn the L-shaped bar. I've put my reactions for the pin support at A. So perhaps I should label these here A and B. So I have a reaction force in the X direction and in the Y direction due to the pin support at A, and I have just a reaction in the X direction due to the roller support at B. And I've put on my dimensions that I know, I've put on a coordinate system, and what I'm going to do for my center of mass calculations is assume that point A is at the origin of my coordinate system. So what I'm going to have is I'm going to have to split this up into two pieces. This is going to have a center of mass, and this piece is going to have a center of mass as well. So let's work out where that center of mass is. So you'll remember when we discussed this before, that if we have like a concave object, remember we talked about like rings and curved lines. The center of mass isn't necessarily on the object itself, and that's what we've got here in this case, right? We're expecting the center of mass of this total object to be somewhere around in here, yeah? So let's break the problem up into two pieces so that we have this piece and this piece separately, and they have these two centers of mass, number 1 and number 2. So to find the x-coordinate of the center of mass, we've seen this formula before. We multiply the x-coordinate of the center of mass by the length of this piece, add it to the x-coordinate of the center of mass of this piece multiplied by its length, and then average it over the whole length. So that's what I've done here. So the x-coordinate of the center of mass of this piece is just halfway along it, right? Because we know A is at the origin, the center of mass is halfway along, so that's at x equals 0.5, right? And this length here is 1 meter. So that's where this comes from. And then here, the center of mass of this piece is at x equals 1, right? Because this is 1 meter long, and this is 1 meter in length as well. And then we average that over the total length, which is 2 meters, to get x equals 0.75. We find the y-coordinate of the center of mass in exactly the same way, but now we find the y-coordinate of the center of mass of this piece, which is at y equals 0, right? Multiplied by the length, which is 1 meter, and the y-coordinate of this piece, which is at y equals 0.5 because it's halfway along. So that's where this term comes from. Average it over the total length, which is 2 meters, to get y equals 0.25 meters. So the coordinates of the center of mass of the whole shape is just at x bar y bar is equal to 0.75, 0.25 meters. So as we discussed when we were looking at this intuitively, the center of mass of the total object is going to be somewhere around here, right? Where this is 0.75 meters and this is 0.25 meters in the y direction. Okay? So now we can consider the weight of this object, this total object, the L-shaped beam, acting at its center of mass. So we're just going to have one force vector acting at this point now, right? So now we're in a position to go ahead and apply our equilibrium equations to this system. So first of all, summing the forces in the x direction, we have positive FAX, negative FBX. So that's where this equation comes from. Summing the forces in the y direction, we'll have a positive FAY, and we will have negative the weight vector, right? So it's 80 kilos. Bar is 80 kilos. We multiply by the acceleration due to gravity, 9.8, right? So that's in the negative y direction. And then I've chosen to sum the moments about A because that gets rid of these two components here. So if I'm summing the moments about A, I will have the moment due to the weight vector of the total object, and that's at a perpendicular distance of 0.75 meters multiplied by the weight, which again is 80 kilos multiplied by the acceleration due to gravity. And that's going to be in the clockwise direction about A, right? So that's why this is negative. And then I have the moment due to FBX, which is in the counterclockwise direction, so it's positive, at a perpendicular distance of 1 meter. So therefore I have a system of 3 equations, 3 unknowns, and I can solve them in the usual way to find the reactions at those supports. So that just shows you how we're now in a position, because we know how to calculate the centers of mass, we can now revisit some of the problems that we've done before, but now include the mass of the object or the structure or the truss or whatever in our calculations to get a slightly more accurate answer. So the final thing for today then is to look at a composite object. So this is a simple composite object made of 2 materials. The first is a tungsten alloy which has a density of 14,000 kilos per meter cubed, and the second piece is made of steel which has a density of 7,800 kilos per meter cubed. We have dimensions of all of these pieces, and we know that it's centered on the x-axis. And the question is to find the x-coordinate of the center of mass of the total object. So now again, just by looking at this intuitively, we can see that the dimensions of these pieces, this is 240 mil by 80 mil, this is also 240 mil by 80 mil, but on its side, right? And this one is almost twice as dense as this one. So we're expecting our x-coordinate of the center of mass to be down here somewhere, right? Closer to the origin really than over here. So again, we use our averaging formula, as we've seen, weighted average formula. We find the x-coordinate of the center of mass of this piece, multiply it by its mass, add that to the x-coordinate of the center of mass of this piece, multiplied by its mass, and then average it over the total mass. So that's what I formulated down here. The mass of the first piece is just the density multiplied by the volume. I have both of those pieces of information. I'm given the density of the tungsten bit, and I can work out the volume by doing base times width times depth, right? And I've written that in terms of meters, converted the millimeters into meters. And I've done that for the second piece as well, right? And then I need to deal with finding the x-coordinates of the center of masses of both of those pieces. So because these two pieces are made up of the density is constant in both of these pieces, and it's centered about the x-axis, I know the x-coordinate of the centroid of this piece is halfway along it, and I know the x-coordinate of the center of mass of this piece is halfway along this, right? So the x-coordinate of the center of mass of the first piece is half of 80 mil, which is 0.04 meters. And the x-coordinate of the center of mass of the second piece is halfway along here, but I've got to remember to add 80 mil to it because I've shifted it across the x-axis, right? So I do half of 240 plus 80, right, to get the position here halfway along the second piece. So once I have all of that information, I can go ahead and plug it straight into this equation, which is what I've done here. X-coordinate at the center of mass of the first bit I worked out to be 0.04 meters. Then I plug in the density and the volume, do the same for the second piece, for this piece, and divide it by the total mass, which is the density multiplied by the volume of both pieces added together, and what I get is 0.097 meters as the center of mass of the total object. So that's it for today. Hope you're all managing to stay safe and healthy. As always, keep checking Canvas for updates and for new videos being posted. Cheers.